Okay, all right, today, let's get the slideshow going. Boom, we're going to talk about the discrete cosine transform, which is an often forgot sort of little brother to the Fourier transform, but it's got some pretty interesting practical applications, and so we're going to kind of just take a look at that and see what we can do with it. So, hold on, I need to move you over here so I can see the chat. There we go. Okay, just an overview of what we're going to talk about. We're going to talk about the discrete cosine transform, what it is, and then basically it breaks out into two different problems. There's what they call the synthesis problem, and then there's what they call the analysis problem, and they all kind of lead to each other, right? The synthesis problem leads to the analysis problem leads to the discrete cosine transform, and we're specifically going to talk about the DCT4 algorithm in this class. So first, let's talk about the discrete cosine transform. So the discrete cosine transform is commonly used in compression of audio and video signals. It's a really popular way of doing signal compression. It's used in MP3s, it's used in JPEGs and MPEGs, and all of them at their core use this discrete cosine transform algorithm. So if you're doing signal compression, DCT is a good place to start. And in this lesson, we're going to build the DCT up kind of from the ground up. We'll start from basic principles, and we're going to end up with a Python function that performs a discrete cosine transform. Now, there are several steps to arriving at a working DCT algorithm. We already kind of talked about this a little bit. First is the synthesis problem. The synthesis problem basically states that given a set of frequency components and amplitude, how do we construct a wave? Which is to say that if I give you the spectrum of a signal, right? If I give you just an array that has, here's all the frequencies, and an array that has, here's all the amplitudes for those frequencies, can you put together a wave using just that information, right? And it's not hard to see how that leads to signal compression, right? So instead of a wave with a whole bunch of data, noise, and all that stuff, if we just had really simple arrays with just the frequencies and the amplitudes across a certain range, we could reconstruct those signals. So then we need to implement the solution to the synthesis problem in Python using NumPy arrays. And then step 3, the analysis problem, which is sort of a step past the synthesis problem, and it's stated here as given a signal and a set of frequencies, how do we find the amplitude of each frequency component, right? So we have the signal, and we have this half of the spectrum. We have the frequency array, but we need to figure out what are the amplitudes of each frequency component. And then we're going to apply some linear algebra techniques to make it a more efficient algorithm. We're going to use matrices and vectors instead of for loops in order to make it quick and efficient. So that's the basic gist of what we're going to do as we build towards the discrete cosine transform. So first, let's take a look at the synthesis problem. So we already stated it, but I'll state it again. It's given a list of amplitudes and a list of frequencies, i.e. basically the spectrum of a signal, construct a signal that is the sum of these frequency components. So put together a wave. And it turns out that it's actually pretty easy to do. So let's take a look at how to do it. So I'm going to pop out of PowerPoint for just a second. I'm going to pull up Visual Studio Code. We've got sort of an empty thing here. So let's say I'm just going to call it demo.py. We've got to add our basic stuff. So I'm going to import ThinkDSP, I think. Check my notes. Yeah, I think DSP as, and I'm going to shorten it to just DSP. I got kind of tired of typing ThinkDSP all the time. I'm also going to import NumPy as MP. And we want to do some plotting, so I'm going to import matplotlib as, or excuse me, .pyplot as PLT. Okay. So let's define our function. So let's make a comment. Do that function. Let's say synthesis. All right, so we'll define it. Let's call it synthesize. And we're going to pass to it amps for amplitudes, the array of our amplitudes, freaks for our frequencies, and TS, right? Our lens space to hold all of our signal. So to put together our components is actually pretty easy, and we get to take advantage of some cool Python syntax. So a lot is going to happen on this line. So components is going to be equal to a list of DSP, so dot coast signals. So it's going to be an array of coast signals that take a frequency and an amplitude for, I'm going to flip it over, amplitude and a frequency in, and we're going to use the zip function, amps and freaks, amplitudes and frequencies. So let's kind of unpack what that statement does real fast, right? It's going to say, let's take all of, so the zip function is similar to the enumerate function, but what it does is it lets us take these two arrays and grab each element one at a time. Don't cry, Keel. I don't think you can do this in C. And then, I mean, not without a lot of heartache. So basically it says what we're going to do here is we're going to go through both of these lists and we're going to grab each of the values one at a time. So we're going to grab the first amplitude and the first frequency, and we're going to grab it, and we're basically just going to build a cosine signal at that point. We're going to store that into an array. So when we're done here, we'll have an array or a list. It's not really an array in Python. It's a list of cosine signals at each frequency and each amplitude. So basically we're going to immediately just take all of those amplitudes and frequencies and get an array, and then we need to add them all up. DSP makes it pretty easy, so we're going to make a signal that is DSP dot sum signal from the components. All right. We're going to revisit what this asterisk means in just a second. So we're going to return signal.evaluate. So we're going to get the, this gets us the y's .ts. An alternate thing we could do here is say y's equals signal.evaluate and return ys. All right, so that's our function. Let's go ahead and test it out. So test case. Let's build an array here. So we'll give ourselves some amps, np.array, and let's just fit it with some values. I'll do 0.6, 0.25, 0.1, 0.05. We'll keep it short, just 4. Although, right, a real-world signal would have a whole bunch more than that. Frequencies. Array, let's just go 100 for the fundamental frequency, 200, 300, and 400. I'm going to come up here to the top and define a frame rate equal to 11.025 kilohertz. And then let's do some stuff. We also need a set of t's. So np.lenSpace. We'll go from 0 to 1 at our frame rate. So we'll create a 1 second wave. And say that wave is equal to dsp.wave. Here this kind of answers Brené's question about how do you make a wave. Right, we can just, once we have y's and t's and a frame rate, I forgot the most important part, man. I forgot the part that matters. The synthesize, right? We need y's equals synthesize amps, freaks and t's, and then we'll make our wave from y's and t's at a given frame rate. And let's go ahead and plot it. So we'll say wave.plot. Let's give some annotations to our graph here. We'll say put a title is a wave from synthesis, plt.x label. Be the time domain, time in seconds. plt.y label. Amplitude in whatever amplitudes. And then I only want to see a little piece of it, so I'll do this. I'll say plt.x limit. And we're just going to take a look at 0 to 0.1, so the first tenth of a second here. And then plt.show. All right, let's run that and see what we get. And look at that, we get a nice, pretty sinusoid-ish wave, right? It's got peaks, but then it sort of gets weirdly warped and has this little sort of ripple here at the bottom. And so we can see that we've got a sort of distorted sine wave, and that sort of just comes from adding together all of those signals. And we see the top amplitude goes all the way up to 1, but the bottom sort of caps off here at negative 0.4. And there we go. We've created a wave from synthesis. I'm going to do a thing real quick. I just want to see, I didn't really look into this. I'm not familiar with pointers in Python. Maybe someone can explain to us all what that means a little bit better, but I want to see if it runs without it. If I just give it the list. Ah, okay, yeah. So you can't evaluate the list. You gotta say, give me the data at the list. Gotta use that pointer. And generate our wave. Okay, so any questions about how we generated this wave signal? Correct, Hunter. Yeah. So it points to the memory. It's a pointer. So it says, "Give me the list, not the memory value of the list." So the sum signal thing knows to go there and grab the stuff. But to be totally honest, I didn't really deep dive into this when I was preparing the lecture, so I don't know exactly, like, critically what's going on here. But I suspect, so Akil asks, or hold on, one thought at a time, right? I suspect that some signal needs like a NumPy array, so it needs, like if you just give it a list, it throws an error. But if you say point to that memory thing, it'll say, oh yeah, we're just going to treat it like a NumPy array, is what I suspect is going on there. But like I said, I didn't deep dive into it. Akil asks, why doesn't this look like a cosine wave? And the answer is because it's not a cosine wave. It's a cosine wave that's made up of these 4 different frequency components, right? It is a wave that has these 4 components in the spectrum, which are causing this distortion in the wave itself. I guess we could have a little bit of fun with it. Let's do this. I'm going to take away. So if we just did, hold on. Actually, I'm going to do this. I'm going to copy that. I'm going to comment these out. I'm going to paste that. And then I'm just going to look at, if we just give it 1 frequency component. We did, but they're all going to add together, right? And they're going to sort of disrupt each other. So if we take them all out, and I just do, so we'll do the first one. So we would expect to see a 100 hertz cosine wave at 0.6 amplitude. Let's see what we get. And that's what we get, right? So we do this, right? And now we get a sine wave, or cosine wave at 0.6 to 0.6. So now let's do this. Let's take it and let's add another component. Let's add 0.25 to it at 200 hertz. And let's see what that looks like. There we go. Now we get this weird kind of ripple business, right? Because we've got that 200 hertz one is going at double the speed, right? So we can sort of still see its peak right here at the halfway points. And we get some, and notice that it blew it up just a little bit too, right? We went from 0.6 to 0.8, right? That means because it's double, there's going to be a peak where they line up, in which case we get what they call in physics class, right, constructive interference. And it's going to go up higher, and then it's going to come back down, but it's going to try to peak because there's another peak in the 200 hertz cosine signal that's going to try to sort of peek its head out, even though there's destructive interference happening. And notice the amplitude went down to 0.04 instead of extending all the way out to negative 0.6. Let me add the next component here, 0.1, cat 300. Whoa, now we got all kinds of weird stuff because now we're getting this like weird like third harmonic business. So it's really warping out the wave. And then if we add, we'll just lose that and bring back our original signals. We got our final distorted thing. So Akil, did that answer your question? The gist there is by adding multiple cosines at different frequencies, we're distorting the signal. By the way, we'll wait for Akil and Edward to finish their questions here. These two lines right here, the synthesized business, for anyone working on the second part of the capstone project, should be very interested in lines 7 and 8 here. Kill says, yeah, but he was expecting that similar harmonics, because they had similar harmonics, that the signals wouldn't distort that much. Yeah. Well, the thing is that we didn't do doubles, right? If we did, here, let's do one last thing. So if we'd 100, 200, what if I did this? 100, 200, 400, and 800. So if I did the even harmonics here, well, that actually, shoot, I think it's way weirder. But what about, let's say, 100, 300, 500, 900. See what that looks like. Harmonics do weird stuff, man. Whoa. Also, the changes in amplitude kind of add some strange stuff to the mix. One, two, three, four. Edward says, so instead of using an exponential as a basis function, we use a cosine, different from the Fourier transform. We just don't have the j sine omega t in our transform integral. Is that the difference here? Yeah, basically, right? We're using the cosine function as instead of the exponential sign, so it makes it different from the Fourier transform. Bashir asks on line 7, what does the freak in zip do? So you're not stating the whole thing. It's 4 amp freak in zip amps and freak. What it basically says is we're going to go, these are two lists, or two NumPy arrays actually, and we're going to say let's pull out the elements one at a time and then feed them to the cosignal function here. Okay, we spent a lot of time here. The last thing I want to do is go ahead and let's take a look at the spectrum. So I'm going to go ahead and comment this part out, and we'll say that spectrum equals wave dot make spectrum. And we don't need to hang on to it, so let's just go ahead and plot it directly. So make spectrum dot plot. Let's add some stuff here. PLT. We'll call it wave spectrum from synthesis. Spelling is hard. Okay. Synthesis. And that should be PLT dot title. PLT dot x label. Frequency in hertz. PLT dot y label. Still amplitude. And PLT.x limit. Because remember, since we have a 11,000 or 11 kilohertz frame rate, our spectrum would go out to that like 5,000. But since our highest frequency is 400, let's just go ahead and cap it off at 500. And PLT.show. So let's take a look at the spectrum. And there we go, basically exactly what we expected. Now things got kind of weird, right, because of the way that the spectrum distorts the amplitudes. But yeah, we've got a peak at 100, the next peak at 200, and a peak at 300, and a peak at 400. So we've got our spectrum there of our signal. So, any questions about what we did here, where we took, we were given arrays of amplitude and frequency, and we reconstructed our wave signal? And like I said, this particular demo is extremely relevant to doing the second part of your capstone project. All right, so let us return to the PowerPoint. All right, just to recap a little bit, I went ahead and included the code in the PowerPoint, but this is all the same stuff that we just looked at before. We got our test case, and we got our signals, right? We got our distorted wave signal there. We got our spectrum that's got 100, 200, 300, 400. And so on. So let's move forward and talk about synthesis with arrays directly, right? So the synthesis approach that we just looked at is really great, but it's not very efficient for large and complex signals, right? We only used 4 frequency components here, right? But a real-world signal is going to have hundreds, if not thousands, of frequency components. So we need to make an algorithm that's a little bit more efficient. So by applying some linear algebra, we can make our algorithm more efficient, right? So here, notice in our code here, what did we do, right? We just for looped through the entire spectrum, right? But that is always never the right answer when it comes to processing large amounts of data. Instead, you want to vectorize, you want to use some linear algebra. So basically the functions that we're going to implement are these two ones, right? We're going to create a matrix M that's got codes here. We'll sort of unpack this real fast. Here's what we need to implement. I have it all way out of order. So we've got a matrix M and an output Y. That's a vector that's going to contain all of our Y's, and it's cosine of 2 pi t. And the outer product of F, we'll talk about what the outer product is in just a second. A here is a vector that contains the amplitudes. That's the amps. T is a vector that contains the times. That's our T's. F is a vector of the frequencies, our freaks. And the sort of cross hairs here is the outer product. And what that's going to do is it's not the cross product. It's very, very similar to the cross product, but it's not the same thing, right? In your linear algebra class or your diffie-q class, you probably learned about dot product and cross product, but very rarely are people taught about the outer product. And what that's going to do is it's going to take T and F and it's going to essentially create a matrix of each of these, where the columns of the matrix are the frequencies and the rows are the times, and each element is going to be the product of frequency and time. So we're going to multiply frequency times time, and we're going to store the whole thing in a big matrix. And then what will happen here is by taking that matrix and using it as a parameter inside the cosine function, we'll do cosine of 2 pi times that matrix, we will get matrix M, which is a big matrix that has the value of cosine 2 pi t f at every single possible frequency. So we're essentially going to take that spectrum and blast it out to a big old matrix. And then here we just have a linear equation, y equals m times a, where a is the amplitude. So we're going to go and throw down, take the dot product there, and get a vector that is all of the y's of our signal. So that's basically like a two-step process that gets us to our solution, right? Instead of having to iterate through everything. Next up, we're going to do it in code. Or does anyone have a question about the sort of concept here? We're basically doing the exact same thing. We're just going to sort of do it in a few monstrous linear algebra steps. Bashir is typing. No, not at all. No, not at all. Even though they use a similar signal. No, it's its own. Yeah, it's just the same symbol. Well, actually, the convolution thing is supposed to be like this, like an asterisk inside a circle. But yeah, the outer product is going to create a matrix of all of the products. All right, let's take a look at VS Code and see what we can come up with. So what we're going to do is create essentially just another synthesis function here. So we're going to call this array synthesis. Function declaration. So we'll define, we'll call it synthesize 2 because we're creative. And we'll pass it all the same stuff, amps, freaks and tees. And now here's what we're going to do. We're going to create a variable first. That is our m. We'll say m is equal to np. So NumPy provides an outer product function called outer. And we're going to give it the tees and the freaks. So this will do that outer product and give us our, actually I take that back. We don't want to do this one yet. We want to make this just our, we're going to call it args for now, because m is what happens after we do the cosine business. So now we have m. M is equal to np. We're actually going to stay away from the DSP functions. So np.cosine of, I lied, we're going to use, let's see, does np have, np does have a pi. DSP has a handy pi2 variable, which is just 2 times pi times our args. So let's unpack that real fast. We did our args, which is the outer product of the t's and the f's, like we saw in the math. And then m is just going to be cosines of 2 pi times every value in that argument, right? So args is going to produce a matrix, and m is going to produce a matrix of those cosines. And then finally, all we have to do is just say y's is equal to np dot dot, so the dot product of m and amps, and return our y's. So there we go. So exactly the same function, and hopefully should return exactly the same stuff, right? Just the only difference here is that here we did this for loop business, whereas here we're going to do some vectorized linear algebra type calculations. And we can use basically the exact same test cases here. I'm just going to comment out ys from the first synthesis function, and I'll say ys equals synthesize 2 with amps and freaks and tees. And then let's go ahead and comment out the bottom one. We'll take a look at the spectrum separately. Get the first one back. And we should get the exact same thing. Let's just say away from array synthesis. So we've done exactly the same thing here in our test case. We're just using our vectorized guy here. Run the code. And there we go. We get a wave that looks exactly like the same as the one that we had created originally. And then let's take a look at the spectrum. So we'll comment that out. Save that. And we should get there. There we go. Basically the exact same spectrum. So like I said, we achieved the exact same thing. We just did it in a much more efficient way. So the new code just has a larger array. No, the new code involves a matrix and involves using linear algebra operations, right? Such as the outer product and the dot product, instead of just looping through a for loop and creating the signal manually. So for just 4 things here, it won't make a big difference, but I would kind of be interested to see if we created like a loop of like hundreds of freaks and amps and we timed them, what would we get? Maybe that would have been a good assignment. All right. Any other questions about this? All right. So let's minimize that. Let's go back to PowerPoint from the current slide. And here's the code that we just saw, synthesize. It's a little bit different because when I prepared this, I wrote everything separately instead of combining it all. But when we're done, we get the exact same sort of distorted cosine wave with our same spectrum at 100, 200, 300, and 400 hertz. So that's the synthesis problem. Let's talk about the analysis problem now. So the analysis problem says, suppose you are given a wave and are told the set of frequencies which make up the spectrum. How would you find the amplitude of each frequency component? That can be kind of tricky. Although it turns out that we've almost already done this in our array synthesis. Let's talk about what that means there. So during array synthesis, we did this. We created our matrix M that had all of the possible values of our cosine waves at the different frequencies, and then we used set y equal to M times A, using the dot product to find out what our y's, right? In synthesis, we were given A and asked to find y. In analysis, we're going to go backwards. We're going to be given y and asked to find A. But the matrix M stays the same in either case. So all we have to do is just sort of flip it over on its head and work it backwards. So let's take a look at what that looks like. First off, any questions about the gist here? We're essentially just going to work this y problem here in reverse. All right. Yeah. Okay. So I'll minimize that. Let's bring this back. Analysis. Function declaration. All right, so let's do this. Let's say f. Define. What am I doing? Analyze. Why can't I spell today? YZE, analyze. And here we're going to give the y's and the f's and t's, right? So we always give the t's, but here we were given the amps and the freaks. Let me use the same terminology. Freaks. So the y's, the freaks, and the t's. Here we're given the amps, the freaks, and the t's. So we're going to work our way backwards just a little bit. But a lot of the code is going to be exactly the same, right? So we're going to say args equals. In fact, I'm not even going to type it, man. I'm going to be lazy. I'm just going to copy and paste it directly. It's exactly the same code. The only thing that's different here is the very last one. Amps is equal to np dot linalg. So NumPy has like a whole linear algebra library, and the easiest one is just to solve the function given m and y's. So we're going to solve for amps, solve for a given m and y. If we go back to PowerPoint real fast, all we're doing here is just solving this equation for a. And then we're going to return amps. All right, so when we test it, let's do this. We really can't plot anything, so we got to be kind of creative. I guess we could plot it if we wanted to. We're going to keep our synthesize to function, because remember, we want to kind of compare it to the amps. So let me comment out wave. And let's bring it all down here. I think I broke something. All right. So we created y's from amps and frequencies and t's. So what we're going to do here is I'm going to do this. I'm going to say y's, or amps, 2 is equal to analyze. And here we're going to give it y's. We're going to give it the y's from our synthesize function. Y's, freaks, and t's. And then we will compare the two. Oh, actually, there's a step I got to do in between. We need to know, because of the way y's comes out, we got to change it just a little bit. We'll say y, we need n is equal to the length of freaks, because we're not going to access these guys directly. We need just some pieces of it. So that's going to be amps 2. And now what we want to do is compare the difference. So I'm going to say print the maximum value of amps minus the absolute value of amps minus amps 2. So there we go. All right, so basically what we're doing is we're reconstructing our amps given a piece of the y's and a piece of the t's and the frequencies, and we're just going to compare and see what the difference was. What was the largest error in our amps function? And if I run that, we got this number right here, right? So the largest error that occurred was 1.33 times 10 to the negative 10, which is basically 0, right? So it's a really, really tiny error. And in fact, what if I did this? What if I said print amps and print amps 2? What would that look like? There we go. We can see here it rounds up for us, but we get basically the exact same numbers when you round up. So here we're able to reconstruct what our amplitudes are from the linear algebra. So, any questions about that? Yeah, no reduced row echelon form. Yeah, you don't have to do any linear algebra. You just got to code it out. Edward asks, is information usually sent via the amplitude? Yeah. So usually the amplitudes are the things you don't know, right? We're not going to actually talk about the compression algorithms directly, but the idea there is that you get like a signal and it's sort of a faster way to take the spectrum, right? Because what we want is the spectrum. We want to store an array of the spectrum, but we're not quite to the Fourier transform yet. We want to do it fast, and we're willing to sort of sacrifice some stuff. So if we're given, the y's and the frequencies, we can sort of guess the amps, and that's a step towards doing the discrete cosine transform. All right, let's go back to the PowerPoint. All right, so we finished that. How much time do we have? Oh, we got a little bit of time left. All right, so we've done that already. We demonstrated the code. Here we got the code here. We got the results. Now the next thing, we need to take a bit of a detour and talk about orthogonal matrices. So our analysis function is good, but it could be a little bit better, right? To improve on it, we need to do a little bit more linear algebra, right? Instead of doing the solve function, we can go a little bit faster. And one way to do that is by just using inverted matrices. So what I mean by that is the inverse of a matrix is written just m raised to the negative 1, and it has the property that the inverse dotted with itself is just the identity matrix. So what we want to do here is to solve the linear equation y equals ma, we want to multiply both sides by the inverse of the matrix. And this is going to give us, multiply both sides by the inverse, gets us the inverse times y is equal to the identity matrix times a, which leaves us with just the inverted matrix dotted with y gets us a. So instead of solving and going through the hoops necessary to solve the linear equation, if we just take the inverse of the matrix and multiply that by y, we just get our a directly, and it lets us get there a lot faster. So like I said, we can quickly and efficiently calculate a equals the inverse of m dotted with y. But unfortunately, we only have m, and calculating the inverse of m is slow and is sometimes even impossible. But if m is an orthogonal matrix, then its inverse is equal to its transpose, and taking a transpose of a matrix is really easily. So what we need to do is pick our frequencies and our t's, our f's and our t's, carefully to ensure that m is orthogonal, right? So we're given the wave signal, and we want to create this sort of compressed version of our wave signal. So what we're going to do is we're going to choose what frequencies and what time points we want to care about. And through that, we can reconstruct the signal. But the point is that we get to choose what our f's and our t's are. And so what we want to do is choose frequencies and time points so that our matrix M is orthogonal. And how do we do that? Well, enter the DCT-4 algorithm. It's exactly what happens here. So DCT-4 is a variant of the discrete cosine transform, which leads us to orthogonal M values, right? So it's designed to give us an M matrix that is orthogonal, so that we can just take the transpose, multiply by y, and get our amplitudes. And this is done by just shifting all of the values of t and s. Oop, that's a typo. That should be fs and ts by half a unit. There we go. So we're going to take all of the values that we would normally pick, and we're just going to shift them over by half a unit. And that gives us an orthogonal matrix. By the way, DCT4 is the fourth, spoiler, of 8 variants of the DCT algorithm, right? All 8 have different particular applications. DCT4 is the one that optimizes for orthogonal values of M. So let's take a look at what that looks like. All right, let's see here. Pull up VS Code. DCT-4. Function declaration. So define, let's call it DCT underscore 4. Hold on, let's see. Yeah. And another thing too is DCT4 just takes, maybe I'm messing something up real fast. Hold on. Yeah, Y's, freaks and t's. And so here's what we're going to do. We're going to say we need an n. We just need to know the length, how many y's that we have. And what we're going to do here is, oh yeah, I lied. I don't need these. Stupid. And all we're going to do, so we're given y's, right? And now we're going to choose what our frequencies and what our t's we want to be. So what we're going to do is we're just going to say ts is equal to, here's the magic, half a unit shifted plus np dot, and just give us a range of values up to n. And we're going to normalize it on n. And then our frequencies, 0.5 plus np dot a range. By the way, just to talk about what a range is for just a second, it says here returns evenly spaced values within a given interval. So basically, we're just going to choose evenly spaced values between, you know, basically we get a matrix, get a vector that's the same length as our y's. And here we're going to divide these guys by 2. And then from there, we're actually just going to reuse our synthesize function and our amplitudes function. So what I'm going to do is I'm going to say y's is equal to, wait, what am I doing? Wait, no, I'm not. Oh, I was looking at the wrong line. No. Okay. So TS and FS, now we're ready to do basically just the analysis stuff. So we're going to say args is equal to np dot outer TSFS, m is equal to np dot cosine of DSP dot pi 2 times args. And then what we want to do is return np dot the dot product of m and ys, and we're going to divide it by 2. And there we go. Let's go ahead and test all of that out. So I am going to comment these 2 lines out and say now that just amps 2 is equal to DCT underscore 4, and here we're just passing it the y's that were created by our synthesize function, but no other information, right? We're not passing it any information about the frequencies or the t's, and then we'll print them out and see what we get. Okay. Oh. Let's see what happened. Line 50. Let's comment that out and see. All right. So let's take a look here. We did something wrong. Because we got 0.6, 0.25, 0.1, 0.05. And then we got a big long array. So what did I mess up? Probably by looking at two different pieces of code at the exact same time. Like YS, that, and that. It's all the same stuff. What happened? Okay, well, I apologize. That's what happens when you do it live. Sometimes it doesn't work. We're out of time. It's 1:50, or excuse me, 12:50. I still haven't changed the clocks on these computers. I will take a look at what is the problem there. And, oh, wait, hold on, I see. I needed to set these guys to be correct in my synthesize function. So I need to do, hold on. Set these to 4, and then synthesize. So we need to make sure we have the same size business here for our synthesize function. Otherwise, stuff happens. Let's run that. And we still got stuff that's messed up. All right. Well, you know, famous last words. It was working last night when I was working on it. So we are out of time. I apologize. We'll pick up right here. We'll talk about what's going wrong on Monday. And I think that is just about it. Yeah, look at that. See, I promised it worked when I did it last time. But I'll take a look and see what the problem is in this code. But I'll go ahead and let you guys go. There is no assignment for this week. Don't forget that the assignment about Bitcoin is due on Wednesday. And I'll see you guys on Monday. Have a good weekend. Be safe. And I'll see you on Monday. Thank you so much. I gotta figure out what's wrong with this code, man. Let me see if I run the one that I prepared ahead of time. Yeah, I'll send it, Jacob. I'll post it in the chat. All right, so this works. So what did I not do here that I did here? Like this. All of that. 2. TS and FS.